Hey folks, this is Caleb James DeLisle, and I want to talk to you about the FasterCrypt competition. There's over $10,000 worth of packet up for grabs for whoever is able to optimize the PacketCrypt algorithm. So welcome back. This is a network steward funded project which is being administered by people in the Packet community, not myself. And the purpose of this project is to make a competition for optimizing the PacketCrypt algorithm. What is the PacketCrypt algorithm? PacketCrypt is the mining algorithm used for mining packet. But why is it complicated? It's complicated because the encryption aspects of the packet algorithm, of the encryption, is mimicking, it's designed to mimic the encryption of packets for VPN. It is almost identical to encryption of Cjdns packets. So because of that, it is a very complicated mining algorithm to optimize. So because of this difficulty and this complexity, in order to level the playing field between all the different miners, we've created a competition so that people can compete to make PacketCrypt more performant. And what's great about this is if you compete, if you participate in this competition, the work that you do is also going to be equally useful for encrypting packets for Cjdns and other projects like it. So I'm going to show you a little bit of the code that you would need to optimize in order to make this faster. And then I'll talk a little bit about the high level of what the rules are and how you would make a submission. So the code here is, and I'm going to open my workplace. So you need to check out the PacketCrypt RS codebase, and this is mostly written in Rust, but there's a little bit of C, and the C is actually the code that matters here. And there's a file called blockmine.c. That file's very important. You need to pay attention to blockmine, and I wanted to start here with the function thread. This function is the thread enters where one of the mining workers starts, and this is mining. In order to competition, you can use a GPU. You'll see in a second why optimizing this for a GPU is complicated, but for now I'll just explain that this code is for CPU and you can use a GPU to optimize it. So what we do here is we are asleep. We wait until we have some work. We're in a stopped state. We're building a condition, and then once we're woken up, then we cycle, we get our state to find out what we should be doing, and if we should be running, then we unlock the lock that we're holding, and then we go into mine opt. And mine opt is the inner, this is the hot code which does the mining. So we go to mine opt, and what happens here, we just have the worker, we have a timer that's just for debugging purposes. We're gonna get the header, and that's a regular block header as per packet, as per Bitcoin. And we're going to copy the header from the global into our header here. And then we set the nonce to our worker ID. This is all pretty boring stuff. This doesn't need to be optimized that much. And then we have this nonce called the low nonce. The low nonce is the one that we're going to roll every time we try a new hash. This high nonce is this one we don't really need to change. So the low nonce is, we take the low nonce, we have to hash the header so that hash contains the high nonce. That's the ID of the worker. That's not something that we're going to have to change. We hash it. That's this is buff32. This is a 32 byte structure. And then so we're hashing it using Blake2B. This is again still not where it gets to be hot code yet. But then once we go into the for loop, now we're into the hot code. So what has to happen here? So what you're looking at here, this is a for. This is doing 4 states. We're doing 4 jobs in parallel in order to take advantage of some of the benefits of doing parallel work on a CPU. So obviously, if you're optimizing this for a GPU, you're going to be using more than 4. But the 4 is just what this code does right now. So we have a result object. And then we call this CryptoCycle blockmine multi. And so I'm not going to go into CryptoCycle yet, but I'm going to say what are the inputs. So we have a state. We have 4 states for each the 4 cycles that we're running at the same time in parallel. We have the 4 states, and those are workspaces. They're 2048 bytes each. Then we have the header hash. That's obviously the input, the low nonce, and so we need to cycle through the nonces. And then we have 2 numbers, a number of announcements that are present, and then we have header and we have header and index. Oh yes, so this is actually a lookup table for finding announcements, and I'll go into that in a minute. So then we have the announcements themselves. So what is this announcements? This is a global that it's going to be provided to you in memory, and it is a very, very large buffer containing data that has been downloaded. So remember, we're doing bandwidth hard mining, and so in order to prove that you've actually downloaded all the data, that is the data. And so you need to access that in memory as fast as you can as you're mining. And then when you win a block, then what you're going to do is you're going to take there are going to be 4 announcements. So these 4 announcements is because there's 4 cycles, not to be confused with the parallel states, which there's 4 of them too. But I'll get into the 4 cycles in a minute, and that those 4 cycles are specific to the PacketCrypt protocol. So we need to have all these announcements which are collected into memory, and then we're going to need to supply them to the miner. And then we have the results. There's 4 results because there's 4 parallel states, and each of these results, I can actually show you the result here. It's going to have the high knots, obviously the low knots, that is the one that we're rolling each cycle. It's going to have the in-memory locations of the 4 announcements that are selected and the logical locations. So you need to know that the logical locations are where the code says that it should be, and the memory location is where when you access it via its logical location, you need to look it up in the index to get to the memory location. And then the job number, which is not really used. So anyway, this is the block mine multi. Then we go through the 4 states, so the parallel states. So this number, we could set this parallel states to 1,000 or something, and we could do a multi-cycle of 1,000, and then we cycle over the 1,000, and we check, has any of them reached is the resulting state. So after running block mine multi, the resulting hash is going to be the first 32 bytes of the workspace. That's where the hash is going to be found. So you check the hash on that state, and you check it against the effective target, which is what is the number to beat. And if it's a fail, then you continue, and if it's a win, then you either you log, or if you're not logging, it doesn't matter. And then you store the low knots, the high knots, and then you call the code that's going to assemble the block, and that's where you've won a share or won a block. So note that we roll the low knots by 4 every time because we're running 4 in parallel. And then when we are assigning the low knots here, we're putting in the low knots plus J because these are cycling over these 4, just so that you're not getting lost in this code. And then this timing is just for computing the hashes per second, and this is just for storing our low knots so that when we restart again, we are not we're not running over the same knots again. So that's. Now I want to dive into the block mine multi, because this is really the core of how this works, and this is what you're going to need to optimize. So we go over our states and we initialize them, and then this is this 4 here, not to be confused with this 4. This 4 is the 4 cycles of the PacketCrypt algorithm. So what happens? We take a number by extracting a data from the state. So we're extracting some random data from the data buffer, and then we are taking that modulo the number of announcements that we have. That is the number of items we have in memory, and that gives us an item that we need to use to include into the hash. That's how we prove that we have those items in memory, is by accessing a random item as selected in memory and then proving that we have it. So that's where we get we're going to store here the logical location, right? And then, so just so that you're following along, K is the parallel state that we're cycling through. J is the cycle of the PacketCrypt. And so in logical location J, is where we're storing the logical location of the item. And then we do a little prefetch because we're hoping that we're going to access the index of that item in order to get the memory location. So the reason why we have an index and the reason why we have a logical location and then a memory location is because these announcements are pulled into memory all the time, and the order of the announcements, the logical locations of the announcements depends on their placement in a Merkle tree. And that Merkle tree is different per block, but we don't want to move all the announcements around in memory because that would require way too much shuffling of memory. So we have kind of like a TLB type of thing, but it's done in software where we have a bounce off an index. So that's what the announcement index is for. Now we try to access the announcement index. Now what we're going to do is we're going to get the announcement. This is for the parallel cycles, the wide cycles. We have 4 pointers, and for each pointer, we're going to, again, we're cycling over k. Remember, k is the parallel states, and then for each one, we're going to get the pointer, and we get the pointer by taking the index of the item j that's at this number, and then we go and we put that as the memory location. So you got the logical location, and then you've got the memory location, and then that gives you the value of that number, which is just an integer. And then we go into our ANNs, which is the big memory buffer. That's the one that we have to pass in from the beginning. Big memory buffer. We go to the ANNs, and that is how we get the item. And then we're also doing, and that the item is the pointer to the item. And then we're prefetching the item just so that hopefully by the time we're actually accessing it. So remember, this cycles this parallel states times. And so we cycle over these times. And hopefully we've prefetched all of them into the cache so that by the time we get to here and we're actually accessing them, then ideally it's a cache. Anyway, now we are going through the parallel states a second time, and this time we are we're going to basically copy it into the state, and then we're going to do computation on that. And the computation's a little bit different if we're on the last one, but other than that, there's nothing else. Now, this is the core of PacketCrypt. This is the core of PacketCrypt, whether you are announcement mining or whether you're block mining. If you're announcement mining, then this ANNs that's passed in, that is arbitrary data. It's data that is created for the purpose of mining that announcement. If you're block mining, the data is the announcements themselves. So this is really how PacketCrypt works. Everything from here and then also the final. That's the core of PacketCrypt. Now this one here, Esmal, this is a unique to the block mining, and this is one which takes actually a lot of time. A lot of time is spent in Esmal, and so Esmal is a great target for optimization. An early thing that people who want to optimize can do this. Now, I'm not telling you anything is really secret here. All you'd have to do is compile PacketCrypt and run it in a flame graph, and you would be able to see that most of the time is being spent in Esmal. So what is Esmal? Well, it is scalar multiplication via the curve 25519. So that is also a part of VPN encryption, but it is used in this case in order to just add this other element to the mining. So what happens in Esmal? I'll just go into it and show it to you what happens, and you'll see that this is libsodium. And so we're just using regular libsodium here. We do scalar mult of curve 25519 base on the second 32 bytes of the state. So byte 32 to 63, and then that gives us a public key, which we're going to use for just a moment in order to compute a shared secret with bytes 0 to 32. And then we're going to place the output in bytes 64 to I think 96. So we're just doing 2 scalar multiplication ops, and that's this. Yeah, I highly recommend trying to optimize this one first. It takes only 64 bytes input and then outputs 32 bytes. It's a very low amount of memory that needs to be moved around, and so this is definitely a great one to kind of cut your teeth on trying to optimize PacketCrypt right there. So the other thing is, so I'm just gonna run right through this. Init is pretty simple, as I recall. So what is init? Init is, we just do the hash expand is a cha-cha-20. It takes an input seed and a nonce, and it just expands that into a bunch of data. And then we call make fuzzable. So I'm not going to touch make fuzzable just yet until we get into update, but I'm going to talk about update in just a second here. So actually, I'm going to talk about final before we talk about update. So final is the final bit, and what happens at the final bit is that we do a Blake2B compression of the entire 2048 byte state, and then we put the result in the first 32 bytes. So that is our final hash. That's the one that has to start with zeros in order to have won the objective of the PacketCrypt mining. So that's final. At final, there isn't really that much to improve. It's just a Blake2B hash. As with init, there isn't really that much to improve. It's just a hash expand that is cha-cha-20, and then we're doing a little mem copy and calling this make fuzzable, which we'll discuss in a second. So now I want to talk about update, because update is really the only one that we haven't touched yet, and this is the core of the algorithm. So update, and the update is also the one that is difficult to compute. So let's see here. Update. Oh, right. So this actually init, go to definition. So init is actually a little bit more complicated in the way it's written here, and the reason is because we're doing the same thing as this init. It's just that this one is doing it on 4 of these things at the same time. So it's actually just unrolled a little bit. So don't be too confused about this init being more complicated than this init. It's just that this init is doing it on the n wide things at the same time. So just so that you understand why that looks like the way it does. This one is doing it just on 1. So that's Paris states that's why init is looking weird like that. So we'll go to update. So update, what is update? So this is where we take the item, that is the announcement, and we take our state, which is our work buffer. We need to make a difference if it's the last one. And what we're going to do is we are going to copy the item into our state. We're putting it at 16s2, so that is byte 32 plus, and then it's 1024 bytes. So we're starting at byte 32 and going forward by 1024 bytes, and that's what we're going to write into our buffer. Then we do make fuzzable and then crypt. Now, I will talk about what make fuzzable is, and in order to talk about what make fuzzable is, I need to explain the crypto cycle header and what is happening in Crypt. So remember I said earlier that what we're doing in PacketCrypt is actually identical to encrypting a packet? Well, that's where if you know about fuzzing and fuzz testing, then this is going to make a lot of sense to you. Basically, when you fuzz test something, you are taking a function that does something and you're just calling it with random inputs that could be anything. Encrypt it, decrypt it. It's a long packet. It's a short packet. It has a lot of additional data. It doesn't have additional data. That's what fuzz testing is, and that's what PacketCrypt is doing. So what make fuzzable does is it just removes any possible request. So the crypt is taking as its input the header of the buffer is a request to encrypt or decrypt a certain length of packet. So what make fuzzable does is it just gets rid of some invalid requests, basically. So it's taking literally random input data and just making sure that input data isn't completely invalid. So now I'm going to show you the header, the crypto cycle header, and this is the header of the PacketCrypt. And so we have a nonce that's 12 bytes long. Then we have this data, which contains version, F, length, T, add additional, length of additional, D, TZC, that's trailing 0 count, unused, and AZC, that's additional 0 count. So then we have the key, which is 32 bytes. So when we are asking to do an encryption or a decryption, we place the key here in this 16 bytes plus 16 bytes. And then when we are done, the first 16 bytes will be overwritten with the Poly 1305 authenticator. So when you're doing Poly encryption, you will have a Poly 1305 authenticator that will be associated with your encryption, and then that authenticator must be attached to the file and sent along with it, and the recipient is able to use the authenticator to verify that the file wasn't, that the message wasn't tampered with on the way from you to them. So what we have here is an explanation of what the crypto header looks like. We have the nonce, we have these little pieces of data here, and we have the encryption key. This is what we send when we make a request to encrypt or decrypt. And then what we get back once we have made that request is we have a nonce. We have the same data where it's provided some additional information, and then we have the authenticator, which it just overwrites the first half of our key with the authenticator so that we can read the authenticator back. Now, if we are decrypting, then this authenticator will be, we will expect it to match the authenticator that was supplied to us. So this encryption decryption algorithm, you would have to use it very carefully. You would have to kind of handhold it, but you could think of it as like a crypto accelerator where you pass it a message. The beginning of the message is telling the accelerator what to do, and the rest of the message is the actual message. So obviously the nonce, there's the unused stuff. This is the size of the additional associated data, and that this is measured in 16 byte units. The D is to tell us if we're decrypting, and if we're decrypting, then we need to check the Poly 1305 authenticator. This algorithm will happily decrypt messages which have been tampered with. The reason why we have to do that is because we're telling it to decrypt noise, because this is what the mining is doing, is it's fuzzing this algorithm. It's doing random stuff. So because the additional data and the length are defined in 16 byte units, we have the trailing zero count, which is just telling it the number of 0 bytes which are padded onto the end of the message and shouldn't be considered to be part of the message. Then we have the length, and that's also in 16 byte units. So trailing zero count is for the length. Additional AZC, additional zero count, is for the additional additional authenticated data. And then this T is telling us, is set by the algorithm if the length had to be truncated. This is the version of the algorithm. We only use one version. It's just set to what it is. F is the fail flag. When we're doing PacketCrypt mining, the F flag should never be set, but because of the way it's designed so that it could be used in Cjdns, it could be used in a VPN app. So that F is there for so that you could use it if you need it. And then the pad is the field that is just used to make sure that the key is aligned on a 6. Anyway, the encryption key is the key used for the symmetrical encryption. Okay. The Poly 1305 is the reply. Key half is the lower half of the key that hasn't been clobbered by the Poly 1305. So anyway, that's this is the header. This is what's prepended to the message. And so you have the header, and then the additional data, and then any zeros that pad the additional data out to 16 bytes, and then the beginning of the content that needs to be encrypted. So additional data is not sent on the wire, it's not encrypted, but it's authenticated in order to link it to the data. So that's just a thing that would be used for VPN, like to link it to the identity of the session. So the recipient is going to make sure that it's the right session while they're decrypting it. So anyway, you've got the header, then the authenticated data that is not encrypted and is not going to be sent. Then the zero padding at the end of the authentication that gets you to the next 16 byte boundary. Then you have the data. Then you have any zero padding that brings the data to a 16 byte boundary. And that's what it is looking like. So if you've followed this far, what you should understand at this point is that the additional can be different sizes, and the data can be different sizes. So whatever's after the end of the data, for the purpose of PacketCrypt, that's just random. It doesn't matter. It's not going to be updated in the in the buffer, it's in the workspace, it's just going to be left alone. So, and what decides the length? Well, that's also random, because it's just interpreting random data. The first bytes of that random data buffer is going to be interpreted, and that's going to be how we determine what's going to be the length. So anyway, now we understand a little bit of what's going on. Now we can look at make fuzzable, and what make fuzzable is doing is, number one, we're taking a little the Poly 1305 authenticator, which comes back to us, or the key, and moving it back into the data, and that's just to make sure that there's a continuous stirring of randomness into it. That's that mem copy. Then once that's happened, we set the version, we set the failed flag just to make sure, because those should never be non-zero. Then we set the length, and we just make sure that the length is at least 32 blocks, aka 512 bytes long, and then we're off to the races. That's make fuzzable. So now we can talk about Crypt. So now you probably have a fairly good understanding of what's going on. Now we can get into the meat and potatoes here. So number one, we do just a check to make sure that the version is right and it's not failed. We could probably just omit this check for the purpose of mining, but again, we wanted to make this something that could be used for VPN. So then we create a Poly 1305 state, and we are going to initialize that state using our key. And this is how Poly 1305 works. You take your encryption key, you generate some random some data, you create some encrypted data. Basically, you take zeros and you encrypt them in order to get some random data from the key, and then you use that random data in order to compute the Poly 1305 authenticator, and then the other person at the other end, once you've sent the message, they're going to use the key to generate the same random data, and then create the same Poly 1305 authenticator, create the same beginning in order to eventually create the same Poly 1305 authenticator. That's what we're doing when we set up Poly 1305 here. So now we need to, this is the additional data and the additional data length. Remember, we're multiplying by 16 so that our number is in bytes instead of being in chunks of 16. Same with the length. We're multiplying by 16 so it's in bytes instead of chunks of 16. Then we have our trailing zero count and our additional zero count. So that's the stuff to be ignored at the end. And then from there, we're able to figure out where the content begins, which the content begins at the end of the additional data. So the additional data begins at the end of the header, and then the content begins at the end of the additional data. And that's the end of the additional data and the end of whatever 0 bytes are there. So it is on a 16-byte even boundary. So now we need to check if we are in decrypt mode. And the reason why whether we're decrypting or encrypting matters is because if we're decrypting, then we're going to reverse the process. So we're going to first, if we're decrypting, we need to first do the authentication, because we need to do the authentication on encrypted data. That's what we're authenticating. We're not authenticating our unencrypted data before we encrypt it. We are encrypting, then authenticating, or if we're decrypting, we're authenticating, then decrypting. So those two operations just need to be flipped depending on whether we are in decrypt mode or not. Now, if we're not in decrypt mode, we expect that the trailing zeros will be 0. Now, actually, we set the trailing zeros to 0 right here. You'll see a mem set here because we're not in decrypt mode. We can just set those last zeros at the end of the 16-byte boundary of the message. We can just set them to 0 for this purpose. Remember, they're going to be random, and we need to. Poly 1305 wants to work on blocks of 16 bytes, so we give it blocks of 16 bytes. This is when we're not decrypting, we encrypt, then we mask those zeros, and then we authenticate. Now, when we're encrypting, we really don't care if we over encrypt past the end, because the stream cipher, the way a stream cipher works is it just generates random data and then XORs the random data against the message. So if you go past the end of the message, it's fine. Just wipe those last bytes into zeros. So when we're decrypting, it's a little more complicated. So first we need to do the Poly 1305 on the message. So when we're in decrypt mode, we're doing something a little bit complicated here, a little bit unique, a little clever. And this is because, remember, we only copied a part of the message over. And we know that what we're doing here is not going to affect the next cycle because those bytes are actually going to be overwritten by another announcement. So if we're not on the last one, we're skipping a little bit of the encryption. So we're just encrypting the beginning and the end, but we're not encrypting the part where that announcement's placed. So just so that you understand what's going on here, this is a dirty trick, and we could just do this, but this is just reducing the amount of encryption that we're doing. So that's encryption, that's decryption. And then once we get to the end here, we are taking the length of the message, the entire length of the AEAD, the entire length of the message, and then we're putting that into a commitment, and then we're just doing a poly 1305 cycle over that. And then once we've done that poly 1305 cycle, then we're going to be done, and we just do the poly 1305 final and then stick that at the beginning. So that is a cycle that would be able to encrypt a message or decrypt a message for VPN purposes, but in this case, it's just being used for mining. And the FasterCrypt project is about getting this to be something that it can be more performant and potentially implemented on a GPU. So what are the rules? Well, the rules are that if you propose something, if it's faster than the stock code, if it's in any significant way faster than the stock code, you're in the running. And if there are more than one proposals, then the fastest proposal wins, and all of the proposals will become open source at the end of the project. So if you want to apply, if you want to get involved, then you should get on pkt.chat, and you should ask in the PacketCrypt channel about the people who are managing this project. Again, what is complicated about vectorizing this code? So if you're trying to get this on a GPU, what is going to be complicated is that you have different lengths. And so vectorizing is not easy, because when you vectorize, you try to run a lot of things all at the same time, but the things that you're doing at the same time are potentially different, because sometimes you're encrypting a short message and sometimes you're encrypting a long message. So if you could write some kind of a planner, then in theory you could implement that. That would solve the problem. But in any case, that is why it's complicated, why it's a challenge, and why the best implementation so far is the best open source implementation is for the CPU, is because it's just not an easy thing to do. But I think that people could make something a lot faster. I think that this is totally possible, and I'm really thrilled to see what will come out of this, not only for the benefit to Packet of having this increased fairness, but in the reality that when you look at this, you can see that this is going to be very significant for people to be able to use for encryption, VPN. That's something that's very exciting. So I hope that you will take a look at this. I hope that we'll get more submissions, more people proposing things, and I hope that you'll give me a like and subscribe so that I can see you on the next one. Until then, stay awesome.